So today what we're going to continue is to talk about this idea of internal energy and heat. And so let's first step back and say, what is energy? Okay, what is energy? And energy, that's a really bad energy here, is an extensive property that includes the kinetic energy and potential energy of mechanics. Okay, so when I talk about mechanics, I'm talking about like dynamics. You talked about kinetic, potential energy. Those things still work when we're talking about energy. But my question today is that all? And of course, it's not all. I wouldn't ask you if it's all, if it wasn't everything. And what I would do right now is, if I was in class, I would be talking to you about this. This is a fire syringe. Fire syringe. This little piston cylinder device that we will be looking at. And I have a YouTube video that I'm going to show you right now of a fire syringe and seeing how it works. Let's change the source here. Okay, here is our fire syringe. So watch this video here. Same kind of video that I had, a little different look here. But what we're going to do is we're going to put a piece of cotton in this fire syringe, and they're going to take a piece of dowel to put it down there at the bottom. And then you saw what happened there. That was really quick. They put the cap on it and then rapidly compress the system. And then that little fire occurred down there at the bottom. So let's see this again. See how that fire started when that thing rapidly happened, rapidly compressed. So my question for you is, why did this start on fire? Why did this start on fire? Let's get back to my OneNote. Why did this start on fire? Well, kinetic energy didn't change. This fire syringe did not move with a velocity. It did not change kinetic energy of the system. The system's kinetic energy didn't change. The potential energy of the system didn't change. But sure enough, something changed to energize that cotton, and it's a flammable piece of cotton at the very bottom of that. Something had to happen. So what we did was we worked on a system, worked from the surroundings to the system. That fist pounded on the top of that syringe, adding energy, adding work to the system, compressing that rapidly. So what we did is we worked on the system. Work was transferred to a system. And what happened there, the result was the energy increased in the system. But it wasn't the system's kinetic or potential energy. It was something else. It's something that we're going to call internal energy. It was the energy of basically the air internal to the system. And that energy started to get more and more, that work added more and more energy to it. Now, here's where students kind of have a little bit of issue here, because it really is that internal energy is the kinetic energy of the particles. Those particles were hanging around, just bouncing around, not knowing what was happening. And then as that pressure rapidly started to increase, those particles moved so fast. And when they moved faster, their temperature increased. And when their temperature increased to a temperature that was hot enough to light that flammable cotton on fire, that we had that flame. So internal energy is the energy of the particles as they're moving back and forth, the kinetic energy of the particles. It is not the kinetic energy of the entire system as the system moves. It's of a stationary system as those particles are moving inside of there. So that is what we're talking about with internal energy. Now there's other examples here. Okay, if I have a battery, here's my crude battery. Okay, and I have a positive and I have a negative lead onto this battery. Okay, when we charge this battery, that is not changing kinetic energy. It's not moving around. It's not changing height, not changing potential energy. But we can add charge to that, increase the energy of that battery, recharge it so that we can use it in the function. We're increasing the internal energy of that battery. One thing I've kind of talked to you about before, if I have a closed system and I introduce a paddle wheel and I rotate this paddle wheel, I just spin that paddle around and around and around and around. I'm working on the system. The surroundings are working on that system. And those molecules in there are going to start getting beaten around, and they're going to start to get more excited. They're going to have more internal energy. Okay, even if the system is stationary, not having any kinetic or potential energy effects. So we have to add this idea of internal energy to our understanding here. So what I'm going to say here, I'm going to say delta E. And this is, I'm going to say, the overall change in energy. The overall change in energy, and I'm going to do a capital E for energy, is going to be equal to, well, first we have our change in kinetic energy. That's going to apply to it. We also have our change in potential energy that we've talked about already. And now we have to add our new energy, which we're going to say delta, and we're going to do a capital U. And I'm going to do U here, and I'm going to put little bars on the top to note it's a capital U. So here this is kinetic. This is potential. And this U is internal. And it's easy to remember internal energy is U because there's not a U in internal energy. I don't know why we named it U, but that's what we went with. Internal energy, U. Internal energy is stored inside of the material, increasing of that temperature, the excited vibrations of that molecule. It's internal to our system. Look at the air, the particles inside of our system that we're working with. Internal energy. Internal energy is a property. Okay? Just like kinetic, just like potential, just like kinetic, just like potential, it's a property. I need to know that delta. This key here is this delta. Because of this delta here, that's showing you I need to know the final and the initial, subtract those two, and I get the result. Properties, I don't care how they get from point to point. I don't care how that energy changed. I just want to know it did change. So it's a property. Okay? It's measured in joules or BTU, just like kinetic or potential. Wouldn't make any sense for it to be not the same units as everything else. You don't want to have different units for every term. You want to have the same units. Okay? What we often deal with here, we often deal with specific internal energy. Now remember when I was talking to you about specific volume, I said specific is going to tell us something. Whenever we see the word specific, it's going to mean something to us. And specific means you're dividing it by mass. So specific internal energy is going to be a lowercase u, and that's going to be equal to the internal energy divided by the mass. Okay, dividing it by that mass. So you can tell the difference why I make sure that I denote the capital U with a lowercase u. All right, so this is going to have units of BTU per pound mass or joules per kilogram, okay, or kilojoules per kilogram or something of that nature. Now we could put this on a molar basis, and we will from time to time. You'll put a U, and then what do we do for a molar basis? We put a bar over the top to denote that it's a molar basis, and this is going to be BTU per pound mole or joule per kilomole. Okay, so that's what we were going to do there. Right now, let's talk about a mass basis. That's what we're going to do for most of our time here, is talk about things on a mass basis. Okay. Internal energy is complicated. Kinetic energy we can measure. We could measure the velocity at point 1, the velocity at point 2. Potential energy we can measure the height at point 1, the height at point 2. But internal energy is a more complicated situation than that. And it involves chemical composition, makeup of the system, and it's not easily calculated. So what we're going to do for that is basically these appendices that I have in the back of the book that you're going to be dealing with, these appendices and why I want you to print them out. We're going to start learning techniques in Chapter 3 on how to look these up. Basically, somebody has calculated internal energies for us for all sorts of different situations, and then we're going to learn how to look those up so we don't have to make that calculation every time, which is a welcome relief. But now in Chapter 2, before we get those techniques that we're learning in Chapter 3, I'm just going to give you internal energy. I'm going to say, here's the internal energy at state 2, or here's the internal energy at state 1. Find the remaining unknowns in our first law. Or we'll ask for everything else and tell me what is the change in internal energy of our system. Okay? In change in internal energy, see, delta U, capital U, we could write that as the internal energy at state 2 minus the internal energy at state 1. Or we could write this as mass at state 2 times the specific internal energy at state 2 minus the mass at state 1 times the specific internal energy at state 1. Okay? Now, because we're dealing with closed systems, the mass at state 2 and the mass at state 1 are going to be the same. And so we often write this as delta U is equal to just the mass times U2 minus U1. Now, often students get too lackadaisical with this and they start thinking, well, okay, mass U2 minus U1. Remember, this is the situation where we're dealing with a closed system. Because we're dealing with a closed system, we can take that mass outside of there and we can work with it in that way. So now where we're at is we have a situation where our equation, our first law, looks like this. The change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to minus the summation of all our work. That is our first law that we have to this point. Okay? We'll end right here and take a pause, and we'll go on to our next idea.